One of the last things that you might want to know about a projectile motion problem is the velocity of the projectile, of the object in flight. What's its instantaneous velocities anywhere along the flight? And as we discussed before, well, we have to think of the motion of the object as two separate motions happening simultaneously. So we have the sideways motion, which remains consistent. So if I have the object flying, if I freeze frame it anywhere, the x speed, the speed that it's trying to go forward with, is consistent. Because again, no push or pull in the sideways direction. As you're falling, gravity is pulling you downward, so the downward motion is getting faster and faster and faster and faster. Now, I'm going to get rid of my acceleration arrow here. I'm going to use red again, but with the red, I'm going to represent the y velocities along this pathway, along this parabolic arc, as the object is traveling. So if the object is traveling here, right as soon as it leaves the table or the edge of the cliff, there is no Vy speed. It barely is just starting moving downward. But as I move, and if it's falling, if it's moving sideways but also falling, when I get here, the Vy is starting to pick up speed. And then of course when I get here, the Vy, it's falling, it's getting faster and faster. And then right before I hit the ground, I would assume that Vy is really picking up speed and approaching whatever maximum speed it's going to have. And so a lot of the questions will be like, well, what's the velocity right as this, or right before this object hits the ground? Okay. Well, I have two velocities that I have to worry about. I know that it's going to be moving sideways at 4 meters a second. I don't know what its speed or velocity is right before it hits the ground in the vertical way, but I can find that out. And then neither of those actually answers the question, because the question is, well, what is the velocity right before it hits the ground, which would be the combination of these two motions, which is a vector analysis. You need to find the resultant velocity of these two components, and of course that includes finding an angle at which that object is about to hit the ground with. And so we're going to do that now. We're going to utilize information that we've already done in the previous problem and expand on that and find the velocity right before it hits the ground. So I know the x piece of velocity right before it hits the ground is 4 meters per second to the right. The y velocity here, in this particular case, I don't know, but I can find out because that would be y velocity 2. All right, we started off up here. This would be Vy1. We had no velocity in the beginning. And yes, there's some intermediate velocities along the way. I don't care about those. What's the velocity right here? Right before it hits the ground. Now remember, this y velocity here, even though it's traveled sideways, it's as if you had just dropped it from the same exact height with zero velocity from the same exact height to here. So I can find this. Now, what I'm going to do is I will employ that's got to go. There we go. I'll use this formula. I know that we had no velocity at the beginning of flight when it was first released in the up and down motion. And so you're going to get this. And you're going to take the root and make sure that that root works out. Make sure that you're going to root a positive number, which you will here. And if you do this correctly, if I do this correctly, we end up with a number of 7.67. Now, is a root, so there's a positive and a negative value. And in this particular case, which solution is more valid? Well, of course, the negative is more valid because this is moving downward. The reason you get the positive root, again, is because, remember, if this were launched up at 7.67 from this exact spot at that exact speed, it would move up and then come back down at that exact same speed, just the opposite direction, at that given height. But that's old stuff. So, we now know negative 7.67 meters a second. And so here, 7.67 meters a second. I now know the two components of the velocity right before it hits the ground. Now I'm not done. I have to take this information and I have to do vector addition to find the overall resultant velocity and angle. So what I'm going to do, I'm going to get rid of my little reference system there. I'm going to add these vectors head to tail as you're supposed to. I have a lot of students who do the following. They do this, and then they say the resultant is somehow in here. Oh, no. Remember, it's this vector addition, so we're going to take the 4 meters per second, and we're going to add head to tail, the 7.67 meters a second, and we are going to want the resultant velocity, which is from here to here, right? And this is going to be my Vy final. And I say V2, because that's my final velocity. It's not the x component, it's not the y component, it's just the overall velocity. And I'm going to want this angle. And to do this, I'm not going to show the work, you should be able to do this. You're going to do Pythagorean theorem and find the hypotenuse. So if I do that, oopsie. Try this again, hold on. 8.65. Meters per second. I still have to find an angle, and you should probably employ a tangent to do that. And you'll get an angle of 62.5. It's a little rounded, but that's okay. And so we would say that the velocity right before it hits the ground is V2 equals 8.65 meters per second at negative 62.5 degrees, or a lot of books actually say 72.7. Wow, a lot of books will say 62.5 degrees below the horizontal. If I could spell, that'd be awesome. Do not put south of east, because this is not a north, south, east, west problem at all. This is just something falling towards the ground. So north, south, east, west is not appropriate. But below the horizontal or below the x-axis would be fine, because you are going to, as you're traveling, you're coming this way, you're going this way, you're going to smash into the ground at an angle. Now, and to avoid confusion, remember, when we add vectors, it would be head to tail. You can shift that vector over so that you can clearly see how the projectile is going to impact the ground. So, like I said, this is one of the easiest versions of projectile motion problems to do. We'll take you through the next several kinds of layers in upcoming lessons. Thanks.